Okay, so this is the conclusion of the proof of Lagrange's theorem. The last step was, we had the x, y, z, and w, and our initial assumption, the sum of those four squares is MP, where m is the minimal such number that makes that possible, and we know that we're assuming that m is bigger than 1 and m is odd, and we found these A, B, C, and D that are choices of congruence representatives of x, y, z, and w mod m, and the sum of those four squares is k times m, where we saw that k is a natural number smaller than m. All right, so this is again like the proof of the sum of two squares case. We're going to use the algebraic identity that allowed us to reduce to primes and just write a bunch of stuff out explicitly. So if this is mp and this is km, this is m squared kp if I multiply those two things together. But I also get that the product of these two sums of four squares is a sum of four squares in this following way. I just literally copied the identity and written it out, right? So specifically the four things that are squared are ax plus by plus cy cz plus dw. I literally just copied the identity. Then I have bx minus ay plus dz minus cw, cx minus dy minus az plus bw, dx plus cy minus bz minus aw. So it's a little bit ugly, but it is what it is, and it's all explicit enough in a sense, right? And I claim that each term here on the left-hand side is a multiple of m, right? And so we have choices of each of these A, B, C, Ds. They're basically congruent to one of the x, y, z, or w's about m. So we just write out those congruence equations and we just do it by hand, right? So I claim each of these four things is a multiple of m. So let's just write them all mod m. So the first one is ax plus by plus cz plus dw, right? A is congruent to x, b is congruent to y, c is congruent to z, d is congruent to w. So this whole thing is all congruent just to x squared plus y squared plus z squared plus w squared, which is equal to mp, so that's 0 mod m. Right, and the others are all similar. My next one is b times y minus ay plus dz minus cw. All right, so b is so this is by, so this is congruent to, if I just write it all out, yx minus xy plus wz minus zw, right? And this cancels this and this cancels this, so it's just automatically 0 mod m. It's the same for the other terms. I have a cx plus, let me write this as an x so it's a little more visible. Cx, okay? So cx minus dy minus az plus bw, right? And c by choice is congruent to z mod m, so this is a zx. Dw, dy, well, d is the one congruent to w, so this is minus wy. Az, well, a is the one congruent to x, so this is minus an xz. And b is congruent to y, so this is plus yw. And again, everything just cancels out. So zx minus xz, yw minus wy, all 0. And finally, for the last one, I have dx plus cy minus bz minus aw. If I just write up all these things in terms of x, y, z, and w, what they're congruent to mod m, I get wx minus xw over here, and a zy minus a yz over here, so it's all congruent to 0. Okay? Okay, great. So now each of these expressions on the left-hand side, I'm going to call essentially equal to the letters x, y, z, and w. I could have used subscript 0 like we did in the Fermat's last theorem, but I didn't, so I just called them capital, right? But the idea of the method of infinite descent is take a solution to your Diophantine equation. In this case, it's mp equals sum of four squares, and use that to build a smaller solution. And suggestively, I'll write the smaller solution in the same letters, but just with capital versions. All right. So each of these expressions that's squared here on the right-hand side, I want each of those to be equal to my new capital letter, but I want to divide each of those by m. So I'll say that m times x equals this one. So namely, capital X is this expression divided by m. M times y is the next one. M times z is the next one. And m times w is the next one. Right? And the point is that each of these x, y, z, and w's, right, we've checked that these expressions are all divisible by m. So when I divide them by m, I still have integers. Okay. So therefore, I have m squared times k times p is a sum of each of these m times x terms, right? So let's just write that all out, okay? So, right, I only need that one equation, or, well, let me just erase some on this board so I can keep it on the same side, right? So I have this. Okay, I don't need most of this anymore, right? So m squared kp equals the sum of those 4 squares. Each of those things I'm calling m times a new variable. So that's m squared x squared. Well, there's going to be an m squared in each term, so I'll factor that out right away. So it's m squared times x squared plus y squared plus z squared plus w squared. Okay? So I can cancel the m squareds on both sides is the point. And therefore, the sum of the squares of these capital letters, well, this is capital, dang it, capital W. I missed again. I messed that one up. Okay. Capital W squared is equal to k times p. Right? And remember what we said. We said that k was at least 1, and it was less than m. Right? And m was the minimal choice, where it's the minimal multiple of p that's the sum of 4 squares. And so again, this contradicts the minimality of m, and therefore you're done. All right, so we've proven Lagrange's theorem. We've proven this beautiful result. You know, you can tell any of your friends who aren't even math majors or don't know very much about math, you can show them examples of, you know, tell someone, pick a number, maybe 37 or 55, whatever, pick a number and try to, you know, actually subtract some squares of numbers and try to find it as the sum of 4 squares, and ask them, is that always going to be true? Can you always find 4 numbers that the squares of those 4 perfect squares that add up to be any number you want? If you show that to someone that haven't seen it before, I think they'd be quite amazed. It's quite a surprising fact. All right, so that's it for the proof of this classical result. This is the final theorem of the class. But in the next video, just a very short one, I just want to give a few remarks on another problem that's very dear to my heart, which is the natural extension of this, and I just want to say a couple words about that.